So now that we've talked about what the coordination methods are in Java built-in monitor objects, let's go ahead and take a more detailed look at a visualization of using the coordination mechanisms in the context of our synchronized blocking queue. So we're going to take a look at how you would visualize this using the monitor object icons. And as you can see here, this is all just a visualization of the source code. We'll also look, of course, at the source code in more detail too in just a minute, but I want to show you the visualization first because I think it's really important to get the big picture literally in your mind when thinking about interactions between concurrent threads and how they can work and share monitor objects appropriately. Okay, so the first thing you can see here is we have a queue of threads. They're going to be blocked on the monitor object's entrance queue. And let's assume that that's some mixture of calls to put and take. We also, as we'll see as we go through this, could have a queue of threads that are waiting on the monitor conditions wait queue. Remember, there's only one of these things that's shared by all the threads using a monitor object, unlike the way it works with, say, the array blocking queue in Java, which has multiple condition objects. And you can take a look at this link, which I'd mentioned earlier, if you want to see a more thorough discussion about what kind of monitor is implemented by Java's built-in monitor object. So here's the simple bounded blocking queue. As you can see, we're going to have a thread that runs here, and it'll basically just keep spinning, taking items out of the queue. So, of course, the queue will start out being initially empty, so it's going to block at first. And so here it goes. We start out by calling take. That will acquire the lock, because at this point, there's nobody else contending for that lock. And then it's going to go ahead and do this guarded check. So while is empty, we have to wait. So this is the guarded suspension pattern. You shall not pass, that kind of stuff. Remember, when we do this, calling the wait method will atomically release the monitor lock and put the calling thread to sleep until it's notified. What happens there from an implementation point of view is that thread, in this case thread T1, will be parked on the one and only monitor condition for the monitor object, and the lock is released. So now let's kind of switch our attention to another thread. This thing's going to go for I equal 0, I less than 10. It's going to put items into the queue, and it's going to put strings containing the values, basically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, because things are just starting out, we're going to assume the queue is not full because we make it with, say, 10 items, so we should be fine. So the first thing we do is we'll go ahead and enter the monitor object. It'll acquire the lock because there's nobody there, because the other threads released the lock when it went to sleep, parking on the condition. And then it's going to do its guarded condition check. So while the queue is full, we're going to have to wait. Well, the queue is initially empty, so that condition will not be true. So we're going to continue right past the guard. And we go ahead and add the message to the end of the list. And then we call notify all, because again, there's only one monitor condition, and we have to wake everybody up. And then they'll go ahead and use their guard to check whether or not their condition is satisfied. As you can see here, when thread T1 is notified, it wakes up, but it can't get the lock right away, unless the way the scheduler worked was that notify all was called, and then the lock was released, which very well could happen if you're running, for example, on a single core machine. On a multi-core machine, it's likely that thread T1 will, in fact, be awakened. And depending on how quickly thread T2 gets out of the critical section, it might have to block on the entrance queue for a nanosecond or two. But that's just kind of the way that locks work with Java. Not much you can do about that. So thread T2 then releases the lock on the way out of the critical section, and it exits the monitor object. At this point now, thread T1 is back in business. It's been awakened because it was notified, and then it will go ahead and reacquire the lock. And let's assume, for sake of argument, that it's the only other thread at this point, and therefore it'll grab that lock, get in there, and at that point, the queue will no longer be empty, so it'll be able to remove an item from the queue. And that will allow it to go past the isEmpty guard, as we can see here. Once again, we have to call notify all, informing everybody that it may be the case that the queue is now no longer full. And then the last thing we do is we go ahead and return the item. And as I mentioned, when we had talked about this before, it might be the case that this, again, is a little suboptimal, but it's good enough for what we're trying to show here in terms of the behavior and the correct semantics of using the implicit monitor condition and the implicit monitor lock using built-in monitor objects. So finally, the lock is released. We leave the monitor object, and other stuff can happen at that point. So that's the end of the overview of visualizing our Java monitor object coordination example. What we're going to do next, of course, is we're going to look at the source code in detail, but hopefully now you have a better idea of what's going on in terms of how the threads are interacting and how they're using the monitor lock and the monitor condition to do their thing.